different technologies and their impact on our field, and sort of futurism. Where are these new technologies going? What's going to happen to? What can we expect? So look forward to a couple of interesting 15-minute discussions on that. I'll just run through these. Here's what I'd like them to talk to us about. Maybe we can also ask some questions at the end about, quantum computing, we've heard it for years, where's it going? Is this just an excuse for physicists to take our funding away from us? And will on-chip optical become practical? Does it make sense? There are new developments in copper that may push that out to the future, push it out some years. Which is sort of the title of the thing, how do you characterize what's happening to Moore's law? So is it dead? And what's happening to Dennard scaling? It's a sort of corollary of that. And where's proximate computing? Is that a viable future? And finally, something that I think is very interesting to a lot of us, what about new memory technologies? What will they offer us, and how will we have to re-architect things to take advantage of it? Okay, so with that, I'm going to switch over to Fred's stuff. Operate the computer. When I got my PhD, they didn't have computers.
Thanks a lot. So I think we sort of loosely agreed that I would take the role of the sort of rose-colored perspective, but we'll see. And I think that also I sort of have a set of topics here. They're actually made a little bit before that set of questions, but they loosely follow that theme.
I think you need to turn the thing that you gave me on.
Yeah, it's not working either. There we go. It's moving.
It's off.
Yeah, it was on. This was on play.
Okay.
All right. So, I think the goal that we were presented was to present sort of somewhat extreme positions to generate a debate here. So I'm gonna do that. But let me first start with some motivation, which I think was similar to something we had in the first panel, which is we have this this gap between the growth in the sort of data processing, data storage needs that we have, and sort of even the best case sort of optimistic projections for Moore's law. Right? And so I'm just going to start out with the most extreme view that I could take, which is that we're going to use quantum computing to deal with that, right? And the reason I bring this up is that quantum computation is one of the sort of few technologies that we have that promise some sort of exponential gain to deal with that sort of exponential gap that we had on the last slide. Obviously, this is a sort of high-risk, high-payoff kind of proposition. It's been talked about for some time, as Trevor mentions. We actually, somewhat surprisingly, had real physical machines as many as 15 years ago, very small machines. I think what's interesting recently is that we have a lot of investment and engineering that's been going into quantum computation. In particular, there's been a fair amount of hype around this D-Wave machine, which is actually a quantum adiabatic sort of annealing machine, not so much a digital quantum computer as sort of more in the general case that we're looking at. But I think it still gives some notion of the sort of engineering progress that's been made and the sort of scale of machines that can be built. I think right now there's a lot of excitement in quantum computation, in particular in superconducting devices. Over the last couple of years, there has been quite substantial investment by Google, Microsoft, IBM. The federal government has placed $700 million into superconducting devices, as is soon the British government. And actually, interestingly, to some extent, the size of quantum devices or quantum computers that have been built has been a little bit artificially limited by the funding that we receive. Actually, some federal agencies would prefer that we not build out in the open very large machines. The interesting result of that is that recently Google actually purchased one of the groups at UC Santa Barbara by hiring all their people and building them a lab off campus. And the reason for that actually was that that group wanted to build machines of larger than 10 quantum bits. And Google allows them to do that. Their DoD funding did not. So I think we're sort of at the cusp of some great scaling in terms of quantum machines and quantum devices. I think in the next few years, the goal is to build sort of machines on the order of 100 qubits, and looking to scale basically exponentially past that. I think there's quite a lot of optimism in building superconducting devices. So the big question with quantum computation, I think, number one is sort of what can be physically built, what is the scaling, what progress has been made. But the other big question is sort of what is it good for, what quantum algorithms do we have, right? And that is admittedly probably the most difficult thing. Perhaps surprisingly, if you take a look here at this National Institute of Standards has something called the Quantum Zoo. The Quantum Zoo is a collection of all the sort of known quantum algorithms. And so I did a little plot here. If you look over the years at sort of the number of quantum algorithms that exist over time, and that's including variations on certain well-known algorithms, it has been sort of growing quite substantially. I think back in 2000, I remember we were not very high up on that curve yet, and there was a lot of discussion as to where is this going. And I think our DARPA program manager, Mike Foster, at the time was quite optimistic. He said, "Well, this is still early in the development of quantum algorithms. We have a lot more to go." Right? And so I think that obviously there has been a lot of interest in quantum computation in terms of cryptography, but more recently, there's some optimism that we'll have algorithms that are good for search, machine learning, other kinds of sort of pattern and optimization problems. There's a lot more to do here, but there's cause for optimism. Let me just switch gears a little bit. One thing I think that's very interesting near term is the use of quantum devices and quantum coherence to do classical circuits and latency critical computation. Right? And so here's a little device that comes out of HP Labs, which is actually it's an array of ring resonators which are coherent, and it actually does optical packet routing. And the way it does that is that you can do sort of global corner-to-corner routing using the sort of quantum coherence of those devices in a very sort of low latency manner. Right? And so I think that there's a sort of a large, fairly unexplored area of using the sort of things that we would do for quantum computation, but for classical tasks. And I think there should be some interesting impact there. Let me just talk a little bit about sort of impact of emerging technologies on architectural designs. This gets a little bit towards what Trevor was asking in terms of what are new promising memory technologies, what will they do, what would their effect be on memory systems and future architectures. There are certainly, there has been a lot of work in looking at 3D geometries and different kinds of high density and high bandwidth memory systems. One thing that I found very interesting is there's certainly going to be some impact in terms of persistent memories. And what I found is in many persistent memory technologies, there's some unusual dynamic trade-offs that you can make, in particular in terms of the sort of density, endurance, and persistence of storage can be traded with the time to do writes and reads of those devices. And so depending upon the latency requirements and then these density and endurance persistence requirements of your application, there can be an entirely sort of different design for memory systems in a way that we don't expect. So, HP is making a big bet with this machine of theirs, this little 3D block. And one thing that I found very interesting about their application domain is they're, once again, looking at sort of this big data application domain. And the assumption there is that they're going to be looking at a lot of data that's sort of read mostly. And there's not going to be a lot of write or endurance problems with their memory technology. And they're making a big bet on lots of memristors for density purposes. One thing, I'm taking this a step further, I think there's going to be a large effect of emerging technologies on compute models. Right? And this sort of is going to be in confluence with application trends also and data trends. I think that emerging technologies, well, even CMOS technologies, are going to require that we have sort of error and variation tolerant compute models exposed to the user of the application and the compiler. The challenge, of course, is going to be bounding the sort of desired error and achievable error of those devices, right? The desired error at the application level and the achievable error at the devices. And there's been a lot of work in this area, right? So this new Flex Java paper, I think it does some sort of software level encoding of the desired errors that you want in terms of the approximations you can tolerate. In the sort of big data area, this interesting approximate Hadoop work recently shows how you can use sampling to generate sort of approximate results with some bounded error, given the sort of statistics of storage. And just taking that one step further, when we look at these large big data problems or sort of high dimensional sort of problems that generate big data, we're in this situation where we're in a sort of energy and often time constrained computation where you just can't cover the entire space or you can't cover the entire data center. Right? And so I think that from an application point of view, there also will be a sort of requirement for approximation. And that one way to look at that approximation is sampling. And a very sort of common technique that's being used in this domain is this notion of importance sampling in computational science and in data analysis. You can think of that as, for computational science, as bias Monte Carlo. The problem, of course, once again, in this kind of approximate computation is bounding the error, right? And this is not. This is tractable if you have a fairly sort of continuous convex space, but if you have something with sort of real world situations that have a fair amount of discontinuities, then you run into this sort of area where you have to do sort of analysis to find discontinuities and sample or sort of provide more precision in those areas of that space. I think there should be some interesting areas here where we can sort of look at the semantics or perhaps the program semantics of applications and try to reverse engineer those discontinuities. So, just let me say that I think that given this confluence of technology and application space, that approximate computation, I think, will become critical for large-scale computations. Okay. So, I don't know if Igor is going to be the Grinch here, but the point here is to bring it, to have a few sort of more extreme points of view and see what we get.
So I do agree that Fred and I are uniquely qualified for this panel. We were funded by this Endowment Quest program with the same program manager, but hopefully our perspectives will be sufficiently different to make it interesting. So I'll start with a couple of straightforward, historical slides, and then try to be more controversial. So over the last 40 years, the electronics industry, did wonders in terms of integration, putting a lot of things on a chip, right? You're literally carrying supercomputers. Someone measured WinPack on iPad 3, and that qualified it as a top 300 supercomputer 20-something years ago. And this is still happening. The progress is still going strong. Even if you look only at hardware, not software or networking. Most of the improvements were due to material advances, and there are quite a few studies showing that it's really the materials that fuel this progress, right? There's also, of course, progress in architecture and circuit optimization, but without materials, we would not see anything similar. It's also obvious that this is not going to last for very long. The most immediate obstacle is optical lithography, which seems like an engineering and cost problem, because you could use electron beam for manufacturing, but that's extremely slow, extremely costly, right? So what other limits are there, and what do you do about that? You don't have to go very far to find classifications of limits, right? And these limits could be broken down into system level, circuit level, device level, material, and fundamental. So for example, Dennard scaling is a system trend, and Dennard scaling is dead. I'm trying to answer Trev's questions. Moore's law, which is more of a device law, is continuing, but it doesn't give us the same circuit level improvements, right? So the geometry is still scaling. It's clear it will continue scaling until 7 nanometer features, and maybe until 2 nanometer, but probably not below that. And there we run into limits that are more fundamental. In particular, atoms give you a very hard limit as to how low you can go. And it's not the size of the atom, it's the distance between the atoms in the crystal lattice. So for copper and for silicon, it's actually not that different. It's something like 0.21, 26 nanometers. So if you look at the thickness of the gate oxide or gate insulator, you get just a couple of atoms. It's, I think, 0.9 nanometers in most recent transistors. And that's a problem. There's another problem, which is the wavelength of the electron, which is also pretty significant, right? So the material limit here is the distance between atoms. The more fundamental limit is the wavelength of the electron. And if you study these limits, again, there are papers that do all this and break things down. There's the speed of light, right? There are all sorts of physical constants. You can derive limits to computation based on these constants, but these limits will be very loose. So is this really useful? Well, perhaps if you look at this paper by Seth Lloyd from way back, Seth Lloyd promises 150 years of Moore scaling, before we reach fundamental physical limits, right? That's ridiculous. But the analysis is very interesting. So for example, he says, what energy is available to a computer of, mass 1 kilogram? Well, it's mc squared, right? So c is a very large number. C squared is an even larger number. And a very small amount of mass gives you a huge amount of energy. You can look at this, saying that you have a lot of energy that you're not using. Even before you get to E equals mc squared, there is nuclear force. There are many things before you start annihilating, electrons and positrons. But you can also turn it backwards and say, well, there's too much heat in chips, right? We'll just convert that huge energy into a very small amount of matter, and heat problem will be solved, right? Of course, no one knows how to do this, and there are some limits to doing that, right? But the gap between what the limits tell us and where we are now is huge, right? So with limits, you can do two things. You could see which limits are tight, and that tells you, don't do that. So if you're getting close to the size of the atom and you cannot go below 1 atom size, or the distance between atoms, you're close to limits. It's a wall. But if you see these huge gaps between energy limits and where you are now, that's an opportunity. Okay? And so I think I'm an anti-Grinch here, right? I'm telling you about opportunities, but very soon I will talk about things that don't really look promising. Now, if you talk about energy, you could ask how much energy do we need to switch one bit, right? And the answer to that is well known. There's a paper from the 1960s by very famous physicists. Basically tell you that the Heisenberg uncertainty in the energy time form, before that paper was interpreted wrong by everyone, but there is a right way to interpret it. And in particular, it's extremely relevant to computation. So if you have 0 and 1 as different energy levels with some delta E between them, then to switch between 0 and 1, and I'm talking about 0 in double quotes and 1 in double quotes. If you spend some time t, then the less the energy gap, the more time you need to spend. And if you want to do it faster, then the energy gap will have to be adjusted, right? That's kind of interesting. And doing things in parallel at the atomic and subatomic level doesn't help you with energy. That's considered in the satellite paper I cited earlier. So there's some interesting conclusions. But also, which devices, which technologies get to these limits? Because we're nowhere close to the Heisenberg uncertainty for switching between 0 and 1. Turns out, if you look at quantum devices used for quantum computing, for totally different reasons, we are very close to those limits. So quantum computing, working with quantum bits, is very energy efficient, right? And the reasons are, to preserve quantum bits in their state, you have to isolate them, insulate them from everything else. And this includes limiting the energy transfer. Okay, so it's very simple logic, but until recently it hasn't really been seriously considered as a motivation to study these devices, at least not in computing, maybe in physics. So if you look at this from a historical perspective, right, we can recall that Feynman gave this very famous talk in 1959 where he pointed out there's plenty of room at the bottom. And today we have to agree that there isn't much room left. We're close to the distance between atoms, cannot go much further, at least not with anything we can think of. But there is a lot of energy at the bottom. We don't know how to use it, either to remove heat or to generate energy for computation, but that's an opportunity. Now, on the computation side, and this is what Fred talked about, quantum computing is commonly attributed to Feynman as an idea, right? And Feynman wasn't actually the first person who alluded to this idea. To my surprise, the first person was Turing. In his 1937 paper that described what we call Turing machines, and described the principle of universality, which is now called the Church-Turing thesis, he stated that, well, every physical process should be modeled by a Turing machine, or simulated in some way, but then he said, well, possibly except for quantum physics, because he didn't see a way to do that. And that was, very, very smart. And also a hint for future generations. So Feynman tried to simulate quantum processes, and he failed miserably for many years. And so he said, let's turn the tables, let's use quantum effects to perform computation, right? And he thought of quantum simulations, maybe also some classical problems. Yuri Marin also came up with similar ideas, but more on the computation side, slightly before Feynman. It turns out that this motivation is slowly going away today, because in the last 10-15 years, there have been amazing steps, amazing progress on quantum simulations. Systems that Feynman, some of the systems he wanted to simulate, now can be simulated in polynomial time and very quickly on actual computers. So he would be very surprised if he lived today. But of course, not everything can be simulated. And there are interesting questions, in particular related to photosynthesis. So some of the motivation that people repeat over and over, if you could only understand photosynthesis and generate energy from the sun more efficiently, that would be great. But we cannot even simulate photosynthesis because it involves quantum effects. Okay? And that is still a hard challenge. But it's a science challenge. It's not an engineering challenge. So far. Right? And I wanted to contrast performance versus power, totally different reasoning for quantum computation, right? And I'll talk about performance, and I'll try to counter some of the points that Fred made. Well, first of all, the D-wave, it's sort of a running joke in the field, right? What can D-wave do? And you see that even the economists, had a chuckle about this. A quantum computer would be slower, faster, or the same, or both at the same time. So with D-wave, you need to know two things. We could talk for hours about D-wave, but two things about D-wave that are least controversial and kind of explain what's going on. First of all, they have excellent physicists. They're doing a lot of great physics, which is also true about the field of quantum information processing. as far as conventional computing go, what their chips can do can be simulated faster on a laptop. I'll just say it again. Whatever the chip does, literally can be simulated on a laptop faster. And if you have GPUs or FPGAs or multiprocessing system, you get orders of speeds. This is all mapped out. And let me see if I can, yeah. So this is the first paper over there. Matthias Theurer in Zurich, ETZ. He is basically the guy doing this work and very convincing results. You can download codes. But there was another person who wrote a simple high-key heuristic that runs on a laptop and is just amazingly fast. Solves the same Ising models that D-Wave solves. Now, maybe D-Wave will come up with a better chip, possible, but it's at the moment their problem, not ours. Now, what about practical quantum computers? So, a number of problems. I don't believe that in 10 years there will be quantum computers on anyone's desk. I don't think they will do any useful engineering tasks, maybe science tasks. Let me explain why. So first of all, and most obviously, the qubits are flaky, they disappear quickly. You need to sort of restore them. And error correction that is needed for this requires much larger circuits. So for example, for Shor's algorithm, not number factoring, you need circuits in many thousands of qubits, which are completely unrealistic today. And Fred was very optimistic about where quantum computers could be with enough money. To which I say, even if you assume Moore's law for quantum computers, which is a huge assumption, completely unreasonable right now, in 10 years, scaling 2x every 18 months, you will not get to the point where Shor's algorithm becomes useful, right? And Shor's algorithm is very dear to my heart. I worked on this. If you need the smallest circuits for Shor's algorithm is now using papers, but I have to admit that even if you get it to work, even if you get all the science done, what is the market for Shor's algorithms? People using number theory-based algorithms for crypto will just use different algorithms, right? Now, the most promising application for quantum computers is quantum simulation. And indeed, there are good questions in science that could be answered by fast quantum simulation. However, if you look at, for example, the D. Shaw Anton computer, which was custom-made to do molecular dynamics, it doesn't account for quantum effects at all because they didn't see enough market for that, right? So they did a study, they were well-funded, they didn't even want to build it. That tells to me that there isn't much market for these quantum simulations. You could get isolated results. Maybe you can solve photosynthesis. Okay. Now, quantum approximation heuristics, basically algorithms that don't promise to solve something exactly, but they give you good results. And that's an interesting idea. And there were some claims recently. There was a result showing a better approximation by a quantum algorithm than the best known conventional algorithm. Guess what happened? People who worked on the classical algorithms for the same problem said, aha, I can do better. And they did in about 6 months. Right, so this competition is still ongoing. Quantum machine learning, Google and Microsoft are mentioning this as a promising direction, but if you look at Scott Aronson's paper about quantum machine learning algorithms, basically the promise is not there. It's a good science project, but you cannot assume that this will work, right? So this was started with an algorithm from MIT that claimed to solve large linear systems on a quantum computer. But if you read the algorithm, and it did when it came out, it doesn't solve linear systems. It only allows you to answer some questions about the solutions to these linear systems, which is a lot less. You cannot get the entire vector, right? And in machine learning, you're dealing with a lot of data. Quantum computers are not great with a lot of data, right? They can answer yes or no questions with high degree of certainty, probabilistic. So I'm negative on the engineering aspects of quantum computing, but as far as science, this is all good stuff, but you have to look at it as science and publish in literature, in appropriate literature. So what is promising? Let me change tracks and look at limits that are not as loose, but limits that are tighter. So here's a limit from a paper by David Fisher from 1988. It makes 3 assumptions. Suppose your switching devices or processors or cores, whatever you like, have limited size. They're not too small, they're not too large, right? If you have a very large transistor, then the information can travel too fast between inputs and outputs. And if it's too small, then you can pack too many of them in unit space. Another assumption is the dimensionality, 2D or 3D, right? most of the limits, surprisingly, don't use dimensionality, they don't account for this. And this is a serious limitation. And then the speed of light. I'm not as much concerned about the actual speed of light, but just the fact that there is a bound, right? You cannot communicate infinitely fast. And the communication time grows with distance, linear. So, the limits that arise from these assumptions. The paper is only 4 pages. You can find it, read it, it's not hard to read. But assume you have a problem with an algorithm that takes t of n time for n-sized input. It turns out if you have an unbounded d-dimensional group of parallel processors, then a lower bound, this is omega lower bound, is the t plus first root of t. Assuming this is one computation, not a million totally independent computations that are completely unrelated. This is very surprising because if you look at the book on parallel computation or talk to GPU guys, they'll tell you that matrix multiplication, integer multiplication can be parallelized, exponentially. Not in 2 dimensions, not in 3 dimensions, not in any finite number of dimensions. Okay. So what does this suggest? Well, if you go from 2 dimensions to 3 dimensions, if it's a circuit, then the speed up is, cubic root of t to the 4th root of t, right? So if you divide, you get the 12th root of t. That's small. And that assumes scaling in all 3 dimensions. That's hard to get. So 3D circuits, they haven't seen that much adoption because you don't scale in 3 dimensions and the technology is difficult, expensive. For memories, this works great, but just putting together a chip on a chip means that the communication between the layers becomes very slow, or relatively slow. High capacitance, the TSVs, the through silicon vias are fairly thick, right? So a better solution is monolithic 3D. And in the next 2 slides, I'll try to explain how this can be done, right? And here's a technology to bet on, right? So it's a mix of carbon nanotube FETs and 3D and a couple of others and emergent memories. So carbon nanotube FETs, right? You roll atoms of carbon into these tubes. Depending on how you roll them, they can be metallic or semiconducting, and you get significant benefit in the energy delay product. But also, so the amazing thing is that many technology limits were overcome recently. In particular, you grow them on quartz, which is non-isotropic, so there's directionality, the carbon nanotubes are aligned. High temperature manufacture is followed by low temperature transfer onto the silicon. Variability is now under control, as my Stanford colleagues tell me. This is a big surprise, big news. And the fact that you can do cold temperature transfer allows you to perform 3D, monolithic 3D stacking without multiple chips. You transfer these nanotubes and you grow the chip, right? This is also fairly new. So they have a chip that demonstrates silicon, active layers of silicon, then resistive RAM, and then CN FETs. And you can stack these CN FETs and you can grow them with very fine interlayer views. To answer Trev's question about memories, you need to use multiple emergent memories, resistive RAM, STT RAM. They have multiple advantages. Compared to DRAM, there's no need to do refresh. Non-volatility saves a lot of energy. But to use them, you need to combine different kinds because they have different drawbacks. Some don't withstand a lot of read-write cycles. Some are not very dense. And this also needs to be combined with very high density interconnect, which you get by 3D stacking. And I think I'm done. Here are a couple of references if you care. Thank you.
So, Fred, come up. Let's start rolling. I'll ask you a couple of questions. So, just to kick it off, Igor, I felt like basically leaving the room after listening to you talk. It's like, it's all over. Thank God I'm near retirement. But and then at the very end you sort of gave us some hope. But I question the volume opportunity, whether you can actually do that realistically in volume. You've got about 4 different new technologies that you're trying to put together. Do you have any thoughts on that or any comment on that?
So I'm doing this work with Stanford. We are collaborating on these vertically stacked chips with multiple technologies, and we don't have a full prototype of a full working chip, but there are some examples of as much as possible to try was tried, and so far the results are encouraged. We also have done simulations at different levels, thermal, mechanical, architecture level. It does check out. The improvements in ADP are multiplicative, which is amazing. You get multiple interacting improvements with delay and energy. So I'm very optimistic about this, although a year ago I was not.
Okay, and then my question for Fred, and then you two can ask each other some questions, is what was your reaction to Igor's less than positive statements about D-Wave and some of the new experimental quantum mechanics?
Well, I think that there certainly has been a lot of skepticism about D-Wave in terms of the practical utility of the machine. I mean, one thing about quantum computation is that you can think of it as sort of a contest of two exponentials. You have certain algorithms that have exponential gain, and you have potentially exponential cost in controlling decoherence and noise in machines. Right? And so there's sort of two approaches to that. One is lots of engineering to bring down the exponential cost of making machines run. And there have been some other, there's a few end runs that people are looking at. There's topological codes and topological machines, technologies, which may dramatically reduce the amount of error correction you need. And there are some sort of, at least for small scale machines, sort of physical techniques that people use to control noise, just sort of globally. And so it's clearly an expensive proposition. In terms of sort of area, number of qubits and energy, as Igor mentions. But it's I think there's quite a lot of effort in terms of controlling those overheads. It's hard to say where that will go. There's in the optimistic view is in 10 to 15 years that those things will be under some control. And of course the other sort of big issue is what algorithms will be developed and how many of those will have exponential gain.
So I noticed we've slipped our schedule today, so why don't I move to take questions from the floor? Yes?
The advocate from Ohio Northern University. The question is, it's been said that maybe quantum dots are successful quantum devices, but they're still silicon-based. But we all know that one of the limits of silicon computation is the power consumption of the thermal wall. Would devices like quantum dots be successful avoiding thermal wall or power wall?
Did you get that?
Yeah, so the question was whether quantum dots as devices will help with power consumption issues. And the answer is that the devices themselves may be more efficient, but power is consumed by interconnect, and there aren't solutions that are nearly as promising in interconnect. Yes, you will reduce half of your chip's power consumption by heroic, improvements of devices, but then what they're going to do with interconnect.
So there was this that QCA work that at Notre Dame where they're basically using the devices as interconnect, but it's fairly expensive, right, in terms of connectivity.
Yeah, you have to bubble through step by step. It takes a long time. The layout is very difficult. And you're not using 3 dimensions for that. You're only using 2.
Some other questions? Go
I
ahead.
want to know if you think carbon nanotube is a good solution for making space. How can we manipulate this carbon nanotube? These are very difficult to manipulate, very expensive, time consuming. Is there any solution for that, or is there any real processor that has been made using these carbon nanotubes, or we just made one single switch out of it?
Yeah, so the Stanford guys made a full processor. And this processor was even demonstrated driving a hand that would shake other people's hand, just as a demonstration. So it was a small MIPS processor that was Turing complete, I think, within the last 2 years. As far as other problems, there were a number of advances, some surprising. So I've got in the slides, but I didn't describe. For example, a big challenge is sorting out metallic from semiconducting nanotubes. And this is done by burning metallic nanotubes with high voltage. So it was a trick they came up with. Before that, there was no solution. So there are a number of surprising solutions that I think answers your question.
Are those chemically fabricated?
They are grown chemically on surface of quartz and then transferred mechanically onto silicon at low temperature, which supports 3D, monolithic 3D.
Question from Boris.
So, Boris Graf, University of Edinburgh. Really interesting talk to both of you guys. Thank you. So, I think this question may be more for Igor, since he's more of a kind of circuits technology person. But you mentioned emerging memory technologies. Can you comment on the state of affairs there? I mean, you know, is PCM, STT-RAM, I don't know, the HP stuff, memristors, is this all sort of the science is done, it's just a matter of getting the yields up and commercializing it? Or are there still sort of real challenges to adoption?
Yes, there are challenges, both technology-wise, circuit-wise, full chip optimization-wise, and in terms of architecture. There are challenges and opportunities that you can address. These memories, they have some serious problems. For example, some memories, they don't support a large number of read writes. So you don't want to put them into caches. You can put them into main memory with some fallback solutions. Other memories can withstand multiple cycles, but they're not as dense, so they make caches, good caches. And you need to redesign the entire cache and memory hierarchy to use emerging technologies. Plus, you need to make sure that interconnect supports high bandwidth transfer, which is provided by 3D. Right? And another improvement is, because you're not using DRAM, the controllers get simpler. Right? You don't need to worry about refresh and the delays. So that's a big improvement. The processor becomes idle, is not idle as often.
But those are sort of architectural aspects. But I mean, is this stuff, I mean, you know, like this is production ready, we're going to see this in the next how many years?
So it does look like it will be production very soon, but so far, the attempts were to replace a single type of memory that we use now with a single emergent type. And that is not the right way to go because they have more drawbacks. If you mask these drawbacks in the entire cache hierarchy, that's a better way to go.
So, I remember in the case of the HP program to develop memristors, the guy was saying volume production in 2013. It's 2050. What happened?
We are not using their technology.
It seems like every 2 weeks there's a new technology, particularly in the memory space. And we go through a period of great optimism, and papers are written, and then it sort of fades, like PC RAM. It's sort of, nobody talks about it in polite company anymore. You know, and they also do that. Meanwhile, we've got these very odd things like DRAM, which needs refreshing, which you make, and flash, which is, you know, a weird technology, but they keep moving on. They've been predicted to die many times, and why is that?
Well, it's a hard problem, right? And people try these point solutions, which, as I explained, you know, are not feasible because these memories have drawbacks. Now, manufacturing each of them is difficult, so you need more research. It seems that this research has happened. So the state of research now is better than before, significantly. And other than that, it's, you know, it's subjective, optimistic.
Well, if you just look at DRAMs, you can put gigabits for a few dollars that work. That's pretty impressive. Where's your, you need, it seems to me these new technologies need a niche, like Flash had, what was it, MP3 players or something. where they really fit that niche, so they got volume production. And then they became, the most common storage medium except for disk. Right?
Well, so compared to flash and even DRAM, these new memories are, they can be denser. So DRAM has known scaling problems beyond 8 nanometers or something like that. The capacitors don't scale any lower. Some of the emerging technologies promise that, plus they're non-volatile. So you get something that is, lower power than DRAM and denser than flash.
I mean, I think the non-volatility is really going to become important, but it's really what Igor mentioned, which is that, if you have sort of this flat standard of you're trying to beat DRAM on a level playing field, that's not going to happen, right? You have to have some sort of architectural adaptation or niche, as you mentioned.
Either that or things really do come to a stop.
Right. But there's some really, the thing, I didn't really elaborate on it, but there's some really interesting sort of architectural trade-offs that you can make in some of these devices. So for example, lifetime is a problem in these resistive RAMs, but one thing that we've looked at is that if you write slowly to these devices, you get a quadratic advantage in lifetime. And so an architectural design would be that we write back to this from last level cache in a sort of, we do these sort of delayed write back switch, which can give you that advantage, right? And so there are other things you can do. You can do iterative writes that give you multi-level storage into a single bit, so you can create essentially exponential time for exponential storage into a bit. So there are a lot of things you can do that you can't do with sort of traditional storage devices, and the question is whether those are going to be used profitably at the architectural level.
Yeah. But technologies do stop. We don't have steam engines now. There's a question. Yeah.
So, Nima Wanaman from Stony Brook University. So I want to echo question 4 on that slide, which asks, will approximate computing find a place in computers? So Fred alluded to it kind of in his slides, but I'm just going to ask, can you elaborate on it, and what kind of approximation do you think is going to become successful, if ever?
Well, I mean, I think that sort of at one level, if you're in a serious sort of constrained situation, which could be, for example, that you have a very high dimensional computation that you just will never have enough budget to deal with, either power or time-wise, then you're going to have some form of approximation, right? And so that's a forcing function. Beyond that, I think that if we can get better bounds on sort of desired and achieved errors on computations, then that will become ubiquitous. And then also, I think that if some of these technologies become adopted, we're going to have sort of inherent variability and error that we have to deal with. So I think there's sort of a confluence of sort of 3 different factors.
Are you talking about software or algorithms and software? Or are you talking about some embodiment in hardware?
I'm talking primarily about software, although I think that there are some, at the device level, there are things that you may not be able to hide or you do not wish to hide.
So I didn't touch upon that in my talk, but as I'm supposed to be the Grinch, let me play that role. So I'm not an architect by training, right? My training is in CAD. I have some background in theory of computation and algorithms. To me, as an outsider, it looks like approximate computing is a very bad name for what you guys are doing, right? So I browsed some of the recent papers. There was a workshop on this. And to me, the associations that come up when you say approximate computing include approximation heuristics. For example, in computer design, graph partitioning is done by approximation. You don't find optimal solutions, that's too slow. But if you approximate, you could solve these NP-hard instances in near linear time with near linear memory. Well known, lots of open source codes available. That's not new, right? In the theory of computation, one of the major results from the 1990s is a fully polynomial time approximation scheme for the traveling salesman problem. It shows that the geometric TSP you can solve up to any precision in polynomial time, right? But the time grows exponentially with the decreased with 1 over epsilon. So that's known. There's a great result for the simplex algorithm for linear programming that says, the simplex algorithm, the worst case time is exponential. But if you just wiggle the inputs at random, then with very high probability, the runtime will be polynomial because exponential worst case examples happen very infrequently. Right? Great result, approximate computation. Does it have anything to do with what is done in architecture today? No. Now, stochastic computing, popular topic these days, fundamental approximate. Quantum computing is probabilistic and also approximate, gives results with some probability. Is this considered approximate computing? No. Now, what is it? What is called approximate computing? It's changing the bit width of data path from 16 bits to 14 bits, and that's been done in design automation. Jason Kong, who was earlier here today, worked on this for at least 10 years. Right? There are algorithms for sizing data paths, providing precisions. Some of the issues that Fred mentioned as research challenges, they have been addressed. Maybe not exhaustively, maybe not in a way that users would find easy to exploit. Right? But you have to connect this to what has been done before, and if you call it the right way, maybe data path sizing, then it looks more convincing.
So I guess it used to be I think, therefore I am, I approximate, therefore I make, right? Okay. Yes, last question.
I want to hear from the panel about the interference lithography. About 10 years ago, they introduced that, and they said that we can, and I saw samples of processors using that. We were able to make minimum feature size of our transistor less than the wavelength of the light. But then suddenly nobody is talking about it. What happened to it? It was supposed to be the technology to let us pass the Moore's law using the current lithography.
So you are asking about the lithography with entangled photons or
Interference lithography will use, instead of one mask in the stepper machine, two masks, and the interference of these two lights will be used for fabrication.
Oh, okay,
and
that's a
it's
simple
much
question.
smaller than the wavelength of the light, so we can have any
Right.
new feature.
There's a simple answer. Double patterning and triple patterning, also using multiple masks, so it costs the same, but just exposing, in sequence, not at the same time, is easier, and it accomplishes almost as much. So there's just a better solution. I thought you were asking about lithography with entangled photons, which is a much cooler thing, but it's kind of along the lines of what Fred was saying, doing things with entangled photons that we haven't thought about before. Lots of such things, but that's not really computation.
Okay, we've come to 5 o'clock, so let's thank the speakers again.